Okay. We're going to come back to quantum. And last time we discussed commutation and then Dirac notation and then how to express operator as matrix. And this time we will finish up the math basis for quantum computing, and that's commutation. Okay, and then we will move on to quantum gate and then teleportation and then quantum communication, all those exciting stuff. So commutation or commutator, you guys have seen the definition before at the quantization of light. The definition is AB commutator is A and minus BA. Okay, and then previously we've show you guys, and also you guys have probably shown this in your homework, is that if A and B are operators, okay, they do not commute. Let me restart my. Okay, so for example, x and position and momentum, they don't commute with each other, and at that time we kind of just show that example to you guys. But right now, because we know that the operators can be expressed as a matrix, okay, this actually will make a lot more sense. For example, if you learn linear algebra, you know that the matrix, you can't switch their order, right? And a very simple example would be, let's say, in general, right, you can, in general, any vector and matrix multiplication, you cannot switch them. For example, if it's 1 by 2, if it's AB times AB, right, this is first column, first row, A square, second column, second row, plus B square. And then if it's reverse, it's AB, AB, then the result is actually a matrix, right? First, oh, sorry, my fault. This is a matrix. First column, first row, A square, first column, second row, AB, BA, B square. Okay, and this one is A square plus B square. So you can see that, okay, if you switch the order, it's not, sometimes it will not even be a matrix at all, right? And then you can find many examples. For example, if you have 0, 1, 0, 0 plus, I think this is, yeah, I think this is also not commute. Okay, let me give you an example that's related to physics. Okay, that the matrix, the first matrix is called Pauli Z matrix. Okay, 1, 0, 0, minus 1. Okay, and then the second matrix is the Pauli X matrix. Later, you guys will see this very often. Okay. These are matrices that used by Pauli to express spin. Okay, you don't need to know that. You just need to know these two matrices. And then you can calculate the commutator, right? The commutator on the left-hand side, if we say commutation sigma z and sigma x, right? The left hand, the first is 1, 0, 0, minus 1, 0, 1, 1, 0. Right, and then commutation, the second part is 0, 1, 1, 0, 1, 0, 0, minus 1. Okay, and then you can quickly run through the calculation, and then you can see that the result, okay, I'm not going to repeat it here, it's in the page 24 of the note. Okay, the result is 2, 0, 1, minus 1, 0. Okay, so what it shows you is that, okay, just in general, when you express, well, in general, operators, they don't commute. And then if that's difficult to understand, you can try to understand it in a way that the operator can be expressed by matrix, and matrix you can't switch signs, switch orders. Now, why do we need to care about this? There are actually several very good reasons. And then the first one is related to measurement. Okay, the first one is related to measurement. For example, you guys know that the uncertainty principle, right? The position and momentum cannot be measured at the same time. Now my question is, okay, what about other things, right? Can you measure momentum and angular momentum at the same time? Can you measure position and energy at the same time? And this is actually all related to the commutation relationship. So the first one is that people use commutation relationship to try to find common eigenvalues, common eigenstates, and this would translate into, let's see, this will translate into translate later into whether you can do the measurement, whether you can measure two quantities and know them at the same time. Okay, so let's say if your Hamiltonian commute with an operator, okay, it means that they are zero, right? The commutation is zero. Then what we can say is that you can find eigenstate per psi n, okay, eigenstate per psi then n, that is the eigenstate of both the Hamiltonian H and then the operator A. Okay, both H and A. And we can quickly prove this to you guys. Okay, we can prove this to you guys, and then let me see. Now we can assume that assume per psi n is the eigenstate of your Hamiltonian H, right? Of your Hamiltonian H. Then our question is, okay, then something you can show is that H, the Hamiltonian, act on A per psi n. Okay, act on A per psi n. You can try to calculate this. And when you calculate this, you can use a commutation relationship, right? If the commutation is zero, it means these two are the same, so that you can flip their order, right? So because they commute, you can switch the order, then you get A, H per psi n, okay? And then for H per psi n, because you already assume that per psi n is the eigenstate of Hamiltonian, then you know that this will give you a number right, a number and times per psi n. And then you can bring this number to the front because it's just a number. Then eventually you get En A per psi n. Okay? So what this tells us is that if you look at it, your Hamiltonian applied on A per psi n equals to a number A per psi n. That means A per psi n is the eigenstate, right, of your Hamiltonian, right? So A per psi n, okay, is eigenstate of eigenvalue En. But then we already know that the eigenvalue of En is per psi n, right? Per psi n is the eigenstate of En, right? Then what's going on here, right? What's going on here? So here is that assuming there's no degeneracy, which means that, you know, for En, the eigenvalue En, there's only one eigenstate. Then what you can conclude here is that then A per psi n, okay, must be the same wave function as per psi n, off by a constant, right? Off by a constant, right? So you can conclude that these two, because they're both eigenstate of this eigenvalue, okay, so they're just off by a number. So if you look at this, right, this is a definition of eigenstate of A, right? Eigenstate of A. So this way you prove that, okay, if two operators commute with each other, then you can find eigenstates that you can find a state that are eigenstate of both operators. And and why is this useful? Or why is this important? Okay, the reason is that you guys remember, right? When we say that, in the general procedure of solving a quantum mechanical problem, right? The first step, of course, is to solve the Schrodinger equation, and the second is that you want to, let's say, you want to measure the physics quantity of A. Then what you need to do is that you need to solve the eigenstate of A again, right? Eigenstate and eigenvalue of A again. Then you know, okay, what are the possible measurable values of A, and then you express your wave function in terms of the eigenfunction of A, and then you apply that probability postulate. So that's very, very complicated, and most of the time people don't want to do that. So then what people do is that, okay, suppose I already know H commute with A, and then I know that, okay, what I want to measure in the system is A, right? So now when I solve the Schrodinger equation, I would try to find the eigenstate, okay, that is the eigenstate of both Hamiltonian and your operator A, right? Because if they commute, you can find the common eigenstates. This way you don't have to solve it again for your operator A. You can just solve it once, and then you can find them both. And in reality, okay, how it works is that you just solve Hamiltonian, and unless you're very wrong, the eigenstate you get, is naturally would be eigenstate of A as well. Okay, if they commute, it will naturally guarantee that. Sometimes it will be off by a number or off by something, or off by a linear combination if there is degeneracy. But if there's no degeneracy, you should just see that immediately. Okay, so this is one thing. And then the second thing, okay, connected to this is the uncertainty principle. And then this is a part that always difficult in the lecture is whether I prove it to you or not. And then I did it in the first time teaching this class, and then half of the class fall asleep, and then the second time I skip it, and then it turns out fine because nobody cares. And then also the other thing is I remember in my quantum mechanics, in my undergrad when I took the quantum mechanics class, and one of the finals is to prove the uncertainty principle, and then I didn't know how to do it, and I turned out fine. Okay, so I guess I would just state what the uncertainty principle is and where it comes from. Okay, so the uncertainty principle is this: if you have two operators A and B, two physics quantities A and B, and then they correspond to two operators A and B, And the uncertainty, okay, of A, let me try to, or let me use this notation. Uncertainty sigma A times sigma B, okay, is greater or equal to absolute value of expected value of the commutation between A and B, okay, divided by 2i. Okay, divided by 2i. This is the uncertainty principle. So what it tells you is that if A and B do not commute, okay, do not commute, then the uncertainty of A times uncertainty of B must be larger or equal to something, which means neither of them can be 0, right? So all you can say, if one is 0, the other one is infinite, okay? And if you're really into this and you want to argue, okay, one of them can be 0, if you're really interested, we can discuss this in office hour, that actually take infinite amount of energy, okay, to do that. There is mathematical proof that you can approach that limit, okay. So let me explain a little bit of how we define uncertainty principle. Well, the uncertainty, I think you guys calculate this in your homework, but the uncertainty, for example, sigma A squared, or sometimes we write down as, okay, is the same definition as standard deviation, okay, in the common measurement. And then the it's A, okay, square, your operator square, and then you take the average, expected value minus A, okay, your operator expected value square, right? So this is exactly the same as when you try to calculate the uncertainty principle. Well, sorry, try to calculate the standard deviation of any measurements, right? You have your measurement x squared, take expected value, average minus average square, okay? And then uncertainty of B, okay, is the same okay, and and the basic idea here, okay, the basic idea here is that you can have many different ways to try to understand why uncertainty principle will happen, okay. The very simple way to understand this is actually because of the first duration of commutation, right? We say that if they commute, you can find common eigenstates of H and A. What that means is that, okay, if your state is already in an eigenstate, then you can first measure, for example, the energy Hamiltonian, and that wouldn't change the state because you're already at the eigenstate. And you can then measure the A, right, for example, positional momentum, you can get that value, and then that still doesn't change your eigenstate, right? So it means that you can measure energy first or position first, or position first, energy second, and this will not change your result. Okay, this will not change your result because they're in the same eigenstates. However, if you're not commute, then you can prove that you can't find common eigenstates, right? So let's say you're in eigenstate of A, right? Then you're not eigenstate of H. Now, if I measure energy first, that will project your state into one of the eigenstate of the Hamiltonian. And that state is not eigenstate of A, right? So when you measure A, you will actually get probability, okay, to get several values. So that's actually a fundamental reason that why you will have this uncertainty principle, okay? And then of course you can also understand it in terms of wave, right? Because if you really have a wave, then there's no way you can exactly know where it is, right? Because you have a wavelength, right? Wavelength is a minimum, your wave occupy at least a wavelength of space, okay? But then this understanding, the the uncertainty principle is actually independent of the fact that you can interpret electron as wave. So Heisenberg get this without knowing the Schrodinger equation. Okay, Heisenberg actually get this first just from the commutation relationship, not from the Schrodinger equation. Okay, and then the proof is just some mathematic tricks, and then if you guys are interested, you can look at it. Took about 20 to 30 minutes to finish. Okay. And so one thing that I guess we use it a lot, but then let me just write it down here. Use this example is if we calculate the uncertainty of position and momentum, right? These are the most widely discussed uncertainties. And what you can get is that you can get sigma x times sigma p, okay, greater or equal to, okay, apply this, x commutation with p, okay, and then 2I, right, and then commutation between x and p, you guys can calculate it. This is IH, right? This is IH. So this is greater or equal to IH. Let's see, this is equal to IH divided by 2I. Okay, is 2 divided by H. Right, so this is the uncertainty principle of the position and momentum. And then if you remember, the position and momentum, has a connection to your electrical field and magnetic field in the quantization of light. So you can actually carry this over, and then you can show that, okay, for a light, there's an uncertainty principle between the electrical field and then the magnetic field. Or you can go even further, okay, if you use quadrature amplitude, in phase, out of phase, and then you can further show there's other uncertainty principles. Okay. Any questions so far? Okay. If no, then we can move on to the final topics before talking about quantum gate next week is the Heisenberg picture. Okay, Heisenberg picture. So there are many ways to to get a motivation of getting into Heisenberg picture. Heisenberg itself developed this independent from knowing the Schrodinger equation, right? So he developed this, and then almost at the same time, Schrodinger developed Schrodinger equation, and they argue a lot about it, and then later, I think it's Pauli or someone proved, well, at the age of 21 or somewhere, proved that these two are equivalent to each other. The reason that we talk about Heisenberg picture is not just to show our respect to Heisenberg, but really is that it solves some fundamental difficulties in calculating quantum mechanical problems. And then the first one, the first one would be the primary one is that, let's say if we in a measurement quantum system, if we are only interested in the expected value of an operator, right? We don't have the capability of measuring the individual values like 1 by 1, 1 by 1, and then knowing the probability of them. Let's say we're just interested in this if expected value, and this is true for a lot of cases. For example, in my lab, we actually just measure the expected values. Okay. So also you can actually just use the expected value to do quantum computing. That's also doable. You don't always need to know the individual values. Then the difficulty of it is that, let me give an example, is that if you want to, let me say this, suppose, okay, you're solving the harmonic oscillator in quantum, and then I give you initial condition for psi t equals 0, right? And then I want to ask you what is the expected value at time t, right? For the for your electron in the harmonic oscillator, and if you want to do this in the Schrodinger equation, Schrodinger picture, it's actually kind of complicated, right? Because first you need to solve all the eigenstates and eigenvalues of the system, right? And then you need to do a mapping, okay, to write down your initial condition as the superposition of all this eigenstates, right? All these eigenstates, and then you need to calculate the expected value, okay, by doing the integration of this, right? So this is actually extremely complicated, and then in some cases, actually, for example, the harmonic oscillator, right? If you don't use the ladder operator, the creation and annihilation operator, there's actually not a good way for us to get the eigenstates, right? So a lot of times it's a dead end if you try to do this in the Schrodinger picture. So the Heisenberg picture, okay, actually shows you that, okay, what Heisenberg's argument is that he doesn't like the idea of wave function, right? Because wave function is something that you cannot measure. So in other words, you might not need wave function at all, right? So Heisenberg is more focused on the things that is measurable. For example, position, momentum, right? He say, okay, despite how you evolve, but then every time if I want to measure average value, I always have an average value there. So instead of building equation of wave, okay, the wave, he built equation for the expected value of the operators, okay. And the way to do this, his original way to do this is relatively complicated. That's why Schrodinger doesn't understand his way. So what we will do is we'll actually do this from Schrodinger equation, and then we derive Heisenberg equation. Okay, that's not the historic way, but then it's easier to show you guys, okay, what the Heisenberg equation is, and then actually work, right? So the for example, if you want to calculate the expected value of A, right, then what you're doing is just doing a inner product of A act on your wave function, and then inner product with the left bracket of your wave function. It's like doing an integral of this, okay? And the idea is, okay, can you express this? Wave function, okay, not solving the Schrodinger equation? And the reason, well, the answer is yes, because we know that the time-dependent Schrodinger equation is this: Hamiltonian act on your wave function equals to IH bar partial t, your wave function, right? And then you can kind of solve this in a if you look at it, right? This is first order differential equals to the function itself times something, right? So this looks like an exponential, right? Solution can be exponential solution. So per psi t, your wave function can be exponential, okay, minus I h bar t divided by h, and then act on psi 0. Okay, act on psi 0. If you do this differential, you will see that it matches this equation. Okay, so and let me just say, this is just a different form of Schrodinger equation. Okay, you didn't solve anything because this thing is very difficult to calculate, especially its operator. How you do exponential on operator is a completely different story, and then there's computation really involved in it. It's complicated. Okay, but then but then we can just ignore all those, and then plug in this to here. Okay, this is often also write down as u t psi 0. Right, it's called propagation of the wave. Okay, then what you get here is that a is equal to, okay, psi 0, right, because you substitute this, and then e to the I h bar t h, right, because left bracket is the conjugate transpose, right, so I minus I become I, and then a, and then e to the minus I h bar t divided by h hat t, sorry, yeah. Okay. So the idea here then become very simple, right? So what if we don't calculate the state, right? We don't calculate the evolution of state, but then instead we calculate the evolution of the operator, right? You can as long as you know how this h act on A, right? Then you can get this. Then you can always calculate this, and then this way you avoid solving the eigenstates of your Hamiltonian. Okay, so actually can work pretty well, and it can work pretty well. And then sometimes people write this down as psi 0. This is u, right? U conjugate. U is the propagation of your wave function. U t a u t psi 0. Okay. Sometimes people write this as the a t. Right, so it's not the evolution of wave function, but the evolution of your operator. Okay, so now the question is, if you want to know the actual evolution of expected value of A, okay, then the easiest way to do is to write down its differential equation, right? dA dt, right? Remember that when we solve position, momentum in Newtonian physics, right? What we always have is differential equation about them, right? Differential of position give you momentum, and then differential of momentum give you acceleration, right? Okay, so the idea is to calculate this by using all this, right? And then let me put it this way. Okay, the calculation is a little bit boring, and then a little bit tedious, and then I want to skip again. And then if you're interested, you can look at it from note 29 to note 30, and there's actually a good reason to do that, right? Like if I do this in person, you guys will have some I don't know, respect to not fall asleep or pretend not falling asleep. Like I'm a master of those. Like I usually do this, and then the teacher will not see my eye, and then I sleep half of my high school. but then, you guys are in computer, you can just switch to YouTube or switch to other things, okay, without me ever knowing it. So, let's just pretend some of you that are interested would read the notes, and then some other people, you don't care, that's fine. The actual answer would be IH, okay, expected value, Hamiltonian, and then A. Okay, and then plus partial t expected value of partial A partial t. Okay, so this A is not this one. Okay, it's not this one. This is the original A. Okay, your operator. So for most of the operator, it's not time dependent, right? Unless, for example, you want to measure, unless, for example, your operator has a changing magnetic field or changing electrical field, then you might have time A, but in most of the cases, you will not. And sometimes you just, if A is time independent, not time dependent, then you simplify this to dA dt equals to I h bar h A. Okay, so then this entire thing becomes extremely simple. You write down your Hamiltonian, okay, you calculate the commutation relationship, then you know how the expected value will evolve, right? Will evolve. So this entire thing is very, very simple. And then let me use the harmonic oscillator as an example, just to show you guys what will happen. And then while I'm erasing the whiteboard, it just occurred to me some other things is that there used to be a debate of if you want good students, do you really need good teacher? And the debate is actually especially well known in Caltech because you guys know Richard Feynman is a great instructor, but then none of his students won Nobel Prize. So that's a great failure in Caltech, because we have every 1,000 students there will be one winning Nobel Prize. So Feynman teaching in Caltech for 30 years, and then probably he's the only one at that time not having a student win Nobel Prize as a Nobel Prize winner. And then the instructor next door, okay, doesn't give a damn to students, and then he has 4 or 5 students winning Nobel Prize. Okay, and then and my theory is that actually in my high school well, it's on camera, so yeah. Anyway, my teacher will not watch YouTube. So yeah, my high school physics teacher is pretty bad, and I never listen to her, and then half of the class doesn't listen to her. But then we now, I think, have 4 or 5 physics professor, okay, from the same high school class. So that's pretty amazing. Okay, anyway, let's come back to here. Oh yeah, the punchline is that if you guys... Nobel Prize for you, Professor. Sorry? I'll win a Nobel Prize for you. Yeah, that's my punchline is that if you guys find me terrible as instructor, you're halfway to your success. Okay, all you need is probably another terrible instructor. Okay, so let's look at the. We have 10 more minutes. We can do this. Look at the harmonic oscillator, right? Harmonic oscillator have the Hamiltonian of kinetic energy plus, okay, plus the potential energy, right? And then let's say if we know that the initial state, okay, is a Gaussian. I think you guys saw this in your homework, one of your homework, right? And then this day is actually quite interesting. later you will see this is a coherence. Well, you will not see this in this class, but then in graduate level class, you will recognize this is a coherent state. Okay, and then our question is, okay, if you prepare your state initially as this Gaussian state, and then you let it go, and then let the harmonic oscillator just oscillate, what is the expected value of x and p, at time t, right? So we already explained that, okay, you need to go through series calculation if you use Schrodinger equation to, at least you need to solve the eigen function, which is very, very difficult. But here, okay, well, all you need to do is to, calculate this commutation relationship. Okay, so you have dx dt, okay, equals I h bar h and then x. And then position will commute with position itself, right? So this half, you don't have to worry about it. You only need to calculate commutation relationship between momentum operator and position, okay? And then you guys will do this in the homework this week, okay? So I will skip this part. And then what you will see is that this equation will give you m dx dt equals to p, right? Give you a definition of momentum, right? It doesn't give you much. But then, okay, you will say, okay, then let me try again. If I try to calculate this, I get momentum. So how about what is the evolution of momentum, right? So you do this again. And then this time you will calculate the commutation between position square and then momentum operator. And then this again will be in the homework. And then let me see if I have that on the note. I think so. Yes, and then this would be minus m omega square, okay, x. Okay, so you have one differential to another, and then differential to this, and come back to that. Okay, then this is a standard couple mode equation, and then you can solve this by doing a second derivative of this equation. Okay, then it becomes dx dt square, right? Second derivative equal to differential of this, and differential of this we already know is this one, right? So this is minus m omega square x, right? And then you know that, okay, m can cancel with each other. So what you get is the second differential goes to itself times minus a negative constant, right? And the solution is cosine and sine, right? The solution is very simple. Equal to a cosine omega t plus b sine omega t. Okay, and then how you calculate a and b is that you use this as your initial condition, right? Then you can calculate the expected value at time equals 0 for position and momentum, right? Each initial condition gives you 1, a and b, okay, give you 1. And then you will ask, okay, if I solve momentum, would I have other coefficient? No, because the momentum is just differential of this, right? The momentum is simply a differential of this, so that when you know this, you actually know momentum, okay? And then you just use these two initial condition, and then you can get the answer fairly quickly. And then from there, you will see that the actual solution here would be, okay, if you use all those boundary conditions at time t, is simply x knob cosine omega t. It's like a classical harmonic oscillator. Okay, you release it at position x knob, and then you do a cosine harmonic oscillation. And then, in case some of you wonder, okay, why is that? It's because the choice of this state is a Gaussian state, and Gaussian state is sometimes referred to as a classical state. Okay, when you have Gaussian state, the solution is most likely to be classical. And then there's an argument is that, well, not argument, you can prove mathematically is that if you use Gaussian state to do quantum computing, you will not have quantum advantage. Okay, so and this is kind of show you, okay, one of the examples show you is that if you use Gaussian state, you get something that's very classical. Okay, and that is all for today. And then next week we'll start talk about quantum gate. Okay, thank you guys.
I had a question on the homework.
Mm-hmm.
So I was for question one. I was fine with A through E, but the expected value of the E field, which equation would we use for to find that?
So do you get to the step where you calculate the expected value of Q?
Yes.
Okay, and then it should be left bracket is 0, right?
Because I got it would be left bracket psi of t, close bracket E field, then times psi of t right bracket. Would that be correct, or is that the wrong?
Yeah, that's correct. And then the psi is, is vacuum, right? So it's psi 0, right? And then
Okay.
yeah, and then the trick here is that you should express Q in terms of A and A dagger.
Okay.
And then in the notes, right, there's it tells you, okay, if A act on psi 0, it gives you 0. A dagger act on psi 0 give you psi 1. And then
Okay.
and then you can quickly calculate all of those.
Okay.
Yeah.
Thank you.
Mm-hmm.
Professor, could you say that again?
Yeah, so so you in the expected value of electrical field, right, what you really need to calculate is the expected value of Q. And then to calculate Q, you can actually use the expression, right, in the notes. You can express Q in terms of A and A dagger.
Yeah.
And then A act on vacuum state, it's 0. A dagger act on vacuum state, it's state 1, right? Then yeah, then you can just simply use this linear algebra to figure out all the things.
Just to be clear, we are talking about the expression where E vector is equal to E to EX, the direction vector, in positive X direction, or like just in general.
Let me see. I guess your E expected value for vacuum state is psi 0, okay, and then EX A Q. I think I let sine to 0, right? Sine kz to 1, right?
1.
Okay.
1, yeah.
Then, right, you're asked to calculate this, right?
Okay.
And then these are just numbers of vectors. You can bring it to the front, right? Q is the only operator here.
Yeah.
Okay, psi 0, Q, psi 0. And then what you should do is that you should express Q in terms of A plus A dagger. Right, there's some coefficient here. You can look it up in the note, right? Because in the note,
Yeah.
Q and P are expressed in A and A dagger, so you can reverse that. And then when you A act on this state, you know what it is, right? Note also tells you when A and A dagger act on the eigenstate, what it would do. Then you can actually get the answer.
In number one, question E,
Mm-hmm.
so it tells us to write down Q in terms of A and A dagger.
Yeah.
So will we go? Do you want us to go through the entire derivation, or do we just have to write down the expression?
Write down the expression. I think it's pretty simple, right? Because you already know Q and P in terms of A and A dagger, right? In the notes.
Yeah, it's in the notes, so we don't have to go through the derivation.
No. You just add those two equations together, you get one. Subtract those two equations, you get another one. Yeah.
Okay.
Mm-hmm.
And for the expected value of E squared, you would just replace E with E squared, right? In the top equation.
Yeah.
Okay.
Yeah. And then, yeah.
Thank you.
Mm-hmm.
Good evening, Professor.
Mm-hmm.